Quick review on hydrostatics of cylindrical shaped walls for ME143 in preparation for exam 1. Let's consider a piece of wall, a cylindrical piece of wall, which in 2D is an arc, and this is our arc right here. And we're going to calculate the pressure, force of pressure on the inside surface of this arc, so the normal end is this way. And of course, when the exact formula for the force of pressure is the integral over the surface area of minus P and dA. Here we consider that the wall as a width of B. So in that case, the easiest to calculate the integral is obviously to move into cylindrical coordinates, in which case n becomes minus ER in the cylindrical coordinate defined by the norm vector ER and E theta. But the pressure varies with depth, and it's rho g z for the gauge pressure. So we need to express its z as a function of of theta, and that's here in this case it's going to be rho 0 sine theta. So that's the theta is here. That's the angle defined, say here. That's theta. And the first thing that we can note is that if we calculate the moment of Fp with respect to O being the origin of our frame of reference here, we note that since dFp is parallel to ER right here, and then this is R, this is the vector R in our moment equation, then we have the cross product here of two identical vectors, which is equal to 0. So the bottom line of this is that the resultant, the total force of pressure, its line of action has to go through O, the origin of the framework. Or in other words, the total force is normal to the surface. Now, let's do a quick direct integration of the force of pressure in integral form. So, first let's consider the horizontal component. This is, here I've written the total force right here. So we are just going to consider this part of the equation. And by using a little trick, which is to say that cosine theta d theta is the differential of d sine theta, we find that directly that the horizontal component is rho g r0 square sine alpha square divided by 2 times the width. Now, as you know, I am not a big fan of direct integration, and I feel that we can always solve a problem, or most of the time solve a problem, with the control volume approach. So let's here consider the control volume in red and identify the forces that are exerted in this control volume. So first we have the force of pressure Fp on of the fluid, so Fp of the fluid on the left of the control volume to the control volume. We have the weight of the fluid within the control volume, W, and we have minus F, which is that force here. So the static equilibrium of a control volume is the sum of the forces is equal to 0, obviously. And so now we can move to just calculating the horizontal component, projecting the sum of the forces equals 0. We realize quickly that Fp is the only component that matter. Now, Fp is the force of pressure on a vertical wall, which in this case, as we know, Fp is equal to let's not start with the 1/2, to rho g h square over 2 times b, and here h is equal to rho 0 sine alpha. So we have this, which is the same as what we had before. So now direct integration along y, it's a little bit more complicated. So now we have rho g r0 sine theta times sine theta ez. And for that, we need a little trick, and the first one is to say that sine theta square is equal to sine theta times sine theta d theta, and recognize that sine theta d theta is a differential of minus cos theta. Then calculating the integral I, big I, of sine square theta, and using integration by part, we can show that I is equal to alpha over 2 minus sine 2 alpha over 4, which leads to the normal component is equal to this expression here, rho g r0 square b times alpha over 2 minus sine 2 alpha over 4. Now let's calculate the same thing now using the control volume approach, and recognizing that we have a bunch of here we have a bunch of quantity added, which is like, well, the height here and the width of that triangle in black. So again, we have equilibrium, static equilibrium, and the only force acting vertically is the weight. The weight is equal geometrically to rho g times the volume of the wedge minus the volume of the triangle. So the wedge is the total, if I use, let's say, this trying to find the best color here, but probably not the best idea. So the wedge is obviously the entire wedge, and the triangle that I'm talking about is just this. So volume of the wedge is alpha over 2 r0 square b, which is a well-known formula, and the volume of the triangle based on the dimension that I've just specified is r0 cos alpha times r0 sine alpha. Now sine alpha times cosine alpha is equal to sine 2 alpha divided by 2, hence the result. And thus with this, we easily get the same formula as we had before, and we have, sorry about that, not the right color, we have the full expression of the force. Again, if you wonder why this is minus F, remember that when we identify the forces, we identify the forces acting on the fluid within the control volume. So here we have the force of the wall onto the fluid. But what we are looking for is F, the force of the fluid onto the wall. So this is minus, in our static equilibrium of the control volume here, this is minus F. So in summary, to use efficiently the control volume approach, you need to define your control volume using vertical surfaces where you can use this expression, which is, sorry about that, wrong button. Now the whole thing is freaking out. Alright, here we go. So using this expression that is in the formula sheet and is supposed to be known. Also a control volume for which the volume is easily computed. Identify all the forces acting on the fluid within the control volume, which means one of the forces is the inverse of what you are solving for, and write the static equilibrium of your control volume. And this is that simple.